the C's. You have all learned the matching coefficients method. The matching coefficients method, recast the right-hand side and let's see, do I have any equation numbers in my notes? No, I don't. Oh, no, I have 411. Okay, I'll use notes 411. All right. So, matching coefficients, you would rewrite this equation with common denominator, which would be this. You would get a polynomial in the numerator, and then you would match each power of s, and you get a system of as many equations as you have C's, and proceed to solve it.
How did you know to split it like that?
Because that's what the partial fractions expansion tells me. That's exactly the whole business of partial fraction expansion.
Oh, okay. I see. Sorry.
All right. So, I'm not going to use that method. It can get very involved, and if you're going to write a system of so many equations for so many unknowns, as you get some partial fractions expansion, with a computer, there is a more effective way of getting those equations without having to sit down and do expansions of powers and then matching the coefficients and have all the chance for it. And we're going to learn that method a bit later, not today, in this class. If you look at one of the books that I have given you as suggested reading, and is it Felix or Juan? No, I don't know if anyone of you has got it. But it's the Stephanopoulos book. If you want a book for readability, that's probably the most readable book that I believe it was in the they give in the syllabus any suggested text if you guys need a text.
You did, but they're hard to find.
Well, anyway.
What was the name of the book?
Stephanopoulos, same as the guy in the news, but no relationship to that guy. Stephanopoulos, George Stephanopoulos. Anyway, you'll see that a method. Anyway, you don't have to go and get it. You'll see that a method. And that method that is in that book has a very, very easy way for getting most of the C's, and in many examples, all of the C's.
No, you don't have any syllabus.
But then, for the rest of the C's, it becomes a nightmare. So it will require, let's say I have, okay, here's what it boils down to. If you don't have multiplicity higher than 1, that method is fantastic. You can tell by inspection every single C. I can immediately write for you every single C, what it is. Okay, if I have all roots are simple roots, as is in our example, okay, it's really quick and easy. So I'll call this the quick and easy method. But if I have, let's say, a fourth order, if I had a root of multiplicity 4, that method would require sequential differentiation of ratios 3 times, which gets increasingly hairy. So it becomes very painful for the terms that have multiplicity higher than 1. So my method is a hybrid method. I'm using the quick and easy method to get as many coefficients as this method will give me without any differentiation. And then for the remaining few coefficients, if any, I'll use the second method that I'll talk to you about. So this is a lot faster than matching coefficients, a lot faster than the whole method in the Stephanopoulos book. Okay? So we'll take a break in a second, but let me just start us up. So the method we're going to find is we'll use a hybrid method. The reality is that in most cases, either all roots have multiplicity 1, or very few roots have higher multiplicity, and usually it will be 2 or something like that. We won't have many real applications where we have a root of 15th order, multiplicity 15. Okay? So this hybrid method will be just a quick and easy part for most applications. So we use a hybrid method that combines a quick and easy method for all coefficients of the highest denominator. So we can have the quick and easy method will get me all coefficients of the highest denominators. And in my notation, which are the coefficients of the highest denominator? Thomas, you're also trying to say it, or?
See?
They're all C's, but which C is it? Is it Nate? Who is trying to? Are they CI? Alright, C's alright. Okay? So, for each term, the coefficient of the highest denominator, this is the highest denominator for each root. If it has multiplicity 1, it's first power. If it has higher multiplicity, whatever is the multiplicity of that. So the CI. So with solving a system of linear algebraic equations, which is what you're doing with partial fractions expansion, but we're setting those differently, and we only have a much smaller system. Let's say I had a 10th degree denominator, and 8 roots have multiplicity 1, and 1 root have multiplicity 2. Partial fractions expansion, you would have to set up 10 equations for 10 unknowns. Well, actually not 10. 10 equations for 10 unknowns. And in this method, you would get immediately 9 of the 10, and then you would have to just solve one equation for one unknown. And solving a system of linear algebraic equations for the rest. That's my hybrid method. And obviously, it's time for a break. So we'll continue after, let's say, 13 minutes. Any